So in this lesson, we are going to look at centripetal force. Now, before we can understand centripetal force, we need to understand centripetal acceleration. So we'll begin there. Centripetal acceleration is often called radial acceleration. You'll see why soon, and both terms are commonly used. So consider a particle shown by the black circle in the diagram describing uniform circular motion. Remember, what that means is that the body in question is going in a perfect circle about a center O, radius r, and uniform circular motion means that it's sweeping out the same theta every second. In other words, it has a uniform angular velocity. So our particle is describing uniform circular motion. We've shown the particle in two different positions. Look at the first position where the tangential or linear velocity is v1. A short time later, the particle has moved round the perimeter a little bit and it's now in the second position, and it has a velocity that is a tangential or linear velocity v2. Now v1 and v2 will have the same magnitude because the circular motion is uniform. So the angular velocity remains constant, and so does the linear velocity in terms of its magnitude. Of course, the big difference between v1 and v2 is that they have different directions, and we're going to focus on that right now. So look at the direction of v1. It's a tangent to the circle at that point. Notice that v1, by definition, must make a right angle with the radius at that point. Similarly, when we get to the new position, a little bit further on, the velocity is v2, same magnitude of course as v1, but look at its new direction. It also makes a right angle with the radius at its particular point. So there we have v1 and v2. A reminder that the angular velocity is uniform, and therefore the tangential or linear velocity must have constant magnitude, but by definition it must have changing direction. Now, if a particle has a changing direction, that must mean its velocity is changing. Not changing in magnitude, of course, but changing in direction. But if a velocity's direction is changing, then the velocity is changing. But if a velocity is changing, then the particle p must be accelerating. So although this particle is going round at a nice uniform angular velocity, same number of radians per second all the time, it must by definition be accelerating. It must be accelerating because its direction is changing. So let's try to work out an equation for that acceleration and discover what its direction is. Well, let's begin by looking at the change in velocity. As you know, in a linear acceleration, the linear acceleration is v minus u over t, and v minus u is the change in linear velocity. So it seems like a good place to begin for our centripetal acceleration to look at the change in velocity. Well, let's call the change in velocity delta v, and of course it equals v2, the final velocity if you like, take away v1, which is the initial velocity. Now remember, I've underlined the v2 and the v1 because we're dealing with vectors. They have the same magnitude. I wouldn't want you to think that v2 minus v1 was 0. In magnitude it would be 0, but it can't be 0 as a vector because the direction is different. So v2 minus v1 then, I'm going to rewrite it as v2 plus minus v1. I hope you agree that v2 minus v1 as vectors is exactly the same thing as v2 plus minus v1. Why am I writing minus v1 as plus minus v1? Well, v2 plus minus v1 is a statement of two vectors being added together. And we know how to add vectors together by vector addition. We can use the tip-to-tail method. So let's draw a diagram then where we will add the two vectors v2 and minus v1. Well, there's v2. Have a look at it. It's the same vector as the v2 shown in the circle diagram. It must be because it has the same direction and the same magnitude, so it's the same vector. Now look at what we've done. I've added tip to tail to v2 minus v1. Now let's focus on that minus v1. Minus v1 should have the same magnitude as v1, but it must have the opposite direction. So look at minus v1, it's pointing sort of down to the lower left of the screen, whereas v1 itself was pointing to the kind of upper right. So there's a vector diagram, a tip-to-tail addition of two vectors, where I'm adding minus v1 to v2. Let's get the resultant. Well, the resultant would be the red vector shown. Notice that there will be an angle between v1 and v2. Now, I'm not going to prove this. It can be done, and you're not required to know it, but the angle between v1 and v2 must be theta. If you look at the original circle diagram, you might be able to infer that just by looking at the geometry of the situation. If not, take it on trust that the angle in between v1 and v2 is indeed theta. Delta v then is the red vector shown. That's the resultant of adding minus v1 to v2. Now, let theta be quite small. So look at the circle diagram again, and imagine making theta smaller and smaller and smaller. Now look at the vector addition diagram, and imagine making theta smaller and smaller and smaller. That's really just the same as letting the time interval between the particle moving at v1 and then reaching v2 be a very, very small time interval. Now looking at the vector addition diagram with the red resultant, if I let theta be smaller and smaller and smaller, would you accept that delta v tends towards pointing towards the center of the circle? It tends towards being at a right angle to v1 and v2. And a line at right angles like that is pointing along a radius, which means pointing to the center of the circle. So if theta is very small, then delta v has a direction towards the center of the described circle, point O. Now, the direction of the acceleration will simply be the direction of delta v, because the acceleration is delta v over delta t. So if delta v points towards the center of the circle, the acceleration vector points towards the center of the circle. Now, if an acceleration vector is pointing towards the center of the circle, it's said to be centripetal. Centripetal comes from two Greek words, which means center seeking. But because it acts along a radius towards the center of the circle, it's often called a radial acceleration. And you'll meet both terms. So centripetal acceleration and radial acceleration mean exactly the same thing. Okay, so here is our vector addition diagram again for reference. There is a short derivation coming up. Here we go. So, all accelerations must be changes of velocity divided by changes of time. So they must be delta v's over delta t's. So our radial acceleration, that small subscript r that you see there, that stands for radial. So our radial acceleration must be delta v over delta t. Now remember, look at the vector addition diagram. Delta v is that change in velocity, which we've now established is pointing along the radius towards the center of the circle. Okay, so the radial acceleration is delta v over delta t. Now, if we let delta t approach 0, vanishingly small, can never be 0, of course, but it can approach 0. Then theta approaches 0 as well. Look at the diagram. So the angle between delta V and both V1 and negative V2 approaches 90 degrees, as I said earlier. Now, it can never actually be 90 degrees, but it becomes vanishingly close to it. If that's the case, then we can say from trigonometry that tan theta equals delta V over V2, because delta V becomes the opposite side and V2 becomes the adjacent. However, as theta is very small, we can use what's called the small angle approximation. And for very small angles, tan theta is approximately equal to theta. You can try this on your calculators yourselves. So tan theta equals delta V over V2 becomes theta equals delta V over V2. Let's rearrange that and we'll get delta V equals V2 times theta. Okay, we're halfway there. Remember that the basic definition of radial acceleration, along with any other acceleration, is delta V over delta t. That's where we started. So we can now replace our delta V with this new expression V to theta. I'm going to drop the subscript and just call it V theta, because the size of the two V's, V1 and V2, is exactly the same. So the radial acceleration is V theta over delta t. Now that's a finite expression where delta t is finite. Now let's introduce our instantaneous approach and let delta t tend towards 0 so that our radial acceleration becomes v into d theta by dt. Okay, remember v is a constant in magnitude. So delta theta, or theta over delta t, becomes d theta by dt. But hang on a minute, d theta by dt is omega. So the centripetal acceleration is equal to v omega. But we already know from an earlier lesson that v equals r omega. So we can replace the v with r omega, and we get that the radial or centripetal acceleration is v squared over r, or omega squared r, two equivalent expressions of centripetal or radial acceleration. These equations are listed in the equation list, but you should of course know them, and you'll get lots of practice in doing so. Okay, so we have a centripetal acceleration, therefore there must be a centripetal force to cause that acceleration. Let's explore that. Well, firstly, this is something which you should become very familiar with, and it applies to all situations of uniform circular motion that you meet. It's worth memorizing this. If a body is describing uniform circular motion, then it must be accelerating towards the center of the described circle. Okay, that must happen. And it follows from that by Newton's second law. Newton's second law, of course, says that any accelerating body must experience an unbalanced force acting in the direction of the acceleration. So, if a body describing uniform circular motion has an acceleration directed towards the center of the described circle, and that's a good phrase to always use, incidentally, the center of the described circle, then there must be an unbalanced force. We'll call it a centripetal force. You could call it a radial force, acting towards the center of the described circle, and that's shown in the diagram. So we're looking at the particle at two different positions in its revolution. One's at the kind of roughly at the 3 o'clock position, and you can see the force causing the circular motion is pointing towards the center of the circle. When it reaches the 12 o'clock position, then the force has changed direction, still pointing towards the center, of course, but it's always centrally directed. So that force F is called the centripetal force. Well, let's apply Newton's second law. F equals ma, where F is the unbalanced force. M is the mass of the object, describing the uniform circular motion. So all we do is we replace A with our centripetal acceleration expression, and we get that the centripetal force is F equals mv squared over r, or m omega squared r. And these are expressions which you will become very familiar with. To sum up, if a body exhibits uniform circular motion, then there must be an unbalanced centripetal force causing that motion. And in many of the problems you meet in circular motion involving centripetal accelerations and centripetal forces, almost always the first stage of the problem is to identify the force which is providing the centripetal force. Okay, I sense that you want a worked example, so here's one coming. So let's revisit our chap on the merry-go-round. He's clearly enjoying himself because he's still there. He has a mass of 70 kilograms and he's still on the same horse 6 meters from the center of rotation. Let's imagine that he's going round at the higher angular velocity of omega is 0.79 radians per second. You are now asked then to do a number of things. Part A, find the centripetal force acting on him. That's the centripetal force, of course, that's causing his uniform circular motion. State its direction, discover its cause, and then a couple of little bits at the end about action and reaction. As usual, do not look at the solutions until you have tried each of these parts yourself. That's by far a much better way of learning because you've got to think. So pause the video now, try these questions, and then return to look at the solutions. Well, in part A, we're looking for the centripetal force. We have two options. There are two expressions for centripetal force F. One of them is mv squared over r, and the other one is m omega squared r. Which one do you use? Well, you use the one which fits the data given. So what do we know? Well, we know his mass m, 70 kilograms, that's fine. We are given his radius of rotation, that's 6 meters, and we're given his angular velocity omega. So it looks like F equals m omega squared r is the best option. So let's use F equals m omega squared r, put in our numbers, and we find that his centripetal force is 262 newtons. Part B, what is the direction of this force? All centripetal forces are directed towards the center of the described circle, always the case. Worth memorizing that phrase, towards the center of the described circle. Now part C is slightly trickier. What causes this force? And you're often asked to discover this in such questions. Well, he's clearly describing uniform circular motion, so he must have a centripetal acceleration and he must have a centripetal force. So what's actually causing that force? Well, something must be either pulling him inwards or pushing him inwards, or theoretically both, I suppose. So looking at his situation, what could possibly be exerting a force in towards the center on this chap? Well, the answer is that it's the horse on which he's sitting, and possibly the pole that he's holding onto, that are pushing him in towards the center of the circle. If you imagine yourself sitting on one of these horses, you might be able to kind of feel that sort of force which is pushing you in the way. Now part D, if we imagine the horse pushing the man in towards the center as the action force, what must its reaction force be to that? Well, if the action force is the horse on the man, you simply invert the object, and the reaction force must be the man on the horse. So just as the horse pushes the man in towards the center, action force, the man reacts to that and pushes the horse out, away from the center. That's the reaction force. And that reaction force, the man pushing on the horse away from the centre, is called the centrifugal force. Centrifugal comes from two Greek words which mean centre fleeing. Finally, what would happen if he did not hold on to the horse and the pole? Well, the centrifugal force would push him outwards and he would fall off. So always hold on when you're on a merry-go-round.